Good morning to all of you. Maybe for 2-3 minutes, please go through what I did in the last class. If you have any doubts, questions, otherwise from the total lecture you can ask. Okay. So are there any other questions?
On the boundaries, we know that the direction of force is on one side, but the displacement, in this problem it is simple, so we know that it is in one direction.
Displacement as a positive quantity, we always assume it to be along the positive coordinate direction at all points. Whereas when you talk of forces across the cut sections, that is positive forces along outward normal to the plane. So that's always the case. That displacements are always, so there were two questions. So one was C0 and C1 continuous elements, and another one was on basically the directions for the forces and displacements. So I'll address while I'm just summarizing what I did in the last class. So are there any other questions? So, pardon? Yeah. That is the minimum required. We can of course go on the higher side. So yeah, are there any? So that's the third question. Any other question? Okay, so let me start. So last class we just started this truss element, and essentially this is to solve this differential equation d by dx of EA into du by dx plus q equal to 0. So this is the second order differential equation, and for this the equivalent integral functional we had written within the element. So rather than again writing for the entire domain, let me write for the element. So what I said was that now we have an entire rod, and in this case the force cross section is cross sectional dimensions are much smaller compared to the length, and there are all forces acting only along the length of the rod. So we have only one displacement, independent displacement component, that is displacement along length of the rod. So then we discretize this into a number of elements. So we said no, that we discretize this into the same, of course the cross section remains same. So we discretize this into a number of elements, and then we were trying to derive the equations for one particular element, so with a local element coordinate system. So we consider, say, this particular element I had drawn its free body diagram, and there is of course the distributed force which is acting on this, and then I said no, there is a reaction force from this particular element at this point, since the outward normal here is along negative coordinate direction. That is, so we are taking this force as positive in this direction. Here there would be reaction from this element at this location, so there is a, let us say that force is Q2, and this is the distributed force which is force per unit length. Then we had also said that no, there is a local coordinate capital X I have used, and the displacement is also positive in this direction, which is u. The value of displacement at this point we said as u1, that is left end of the element, and this is u2. And so we also said that this is the, for the element, this is local node number 1, and this is the local node number 2. So this is what we did, and then I said that the corresponding integral functional for this element was integration now over the element. So we had half of integration 0 to small l, that is, I had said that small l is the length of the element. So let me write little up. So small l is the length of the element. So this is 0 to L Ea into du by dx whole square dx minus integral 0 to L u into q dx, and then the potential of these forces, so which was plus q1 u1 minus q2 u2. So this was the integral functional corresponding to this differential equation, which is written for only this element. Now see what we see here. Highest order we had already done the weak form. So for this problem, primary variable is u. So u need to be degrees of freedom at the in node. So that is what we said, that no, u1 is a unknown variable here, that is value of u at this node. Similarly u2, the value of variable u at this node. These should be degrees of freedom at the in nodes, and subsequently we are going to enforce the continuity of this u across elements. So this type of elements we refer to as C0 continuous. C0 continuous means across the elements only this variable is continuous, its derivatives are not. So C0 continuous, only variable, in this case u, only variables, that is your dependent variables, are continuous. Only variable u is continuous across elements. Continuous across elements, and this we do, these are nothing but basically primary variables. In this case, this is a primary variable. Now you might, for example, if you look at when we go for the beam problem, you see the here, if you see q2 is the force along the displacement u2, so the work done is positive, potential energy is negative with respect to undeformed configuration as datum. So potential is negative of the work done. So here the from the undeformed configuration, this would do a positive work, so its potential is negative. This is going to do a negative work, so its potential is positive. So this C0 continuous means only variables are continuous across the elements. That is when we look at the assembly of elements, and if the variable and its first derivative is are continuous across the elements, that is known as C1 continuous element. If variable, its first derivative and second derivative are continuous across the element, it is C2 continuous element, and so on. So and the sign convention, see, for the displacement, we are always taking displacements positive along positive coordinate direction. So here we have taken a global axis x, so the displacement u is taken as at all points taken as positive along positive x direction. But when we are showing these section forces, so here outward normal is along positive x, so this force is shown along positive x direction. This is also positive section force, but since outward normal is along the negative x direction, so this force is shown, positive cross-sectional force is shown along negative coordinate direction on a negative face, that is outward normal along negative direction. So these are basic sign conventions even you use in the concept of hysteresis. Then the next was, we said, approximation for u. So now we look at, there were three things. One is the differentiability requirement as per the weak form or integral functional. So we see it's a first order derivative here, then it must be a complete polynomial. So keeping that in mind, at least we will have to have a0 plus a1x. Now see, if we want to use more terms, we can do that. So if we want to include a2x square, we can do that. But then we'll have to match the corresponding nodes and nodal degrees of freedom. So this is what we did based on the differentiability requirement. We need at least a linear polynomial. We must have a constant term so that the polynomial is complete, constant plus linear term, that is what we have. And then the next step is, and we also said that primary variables should be degrees of freedom at the in nodes. So in this case, primary variable is u. So we have this u, value of u here, that is u1, and value of u here, that is u2 as degrees of freedom. So that requirement is satisfied. And as you see, now if we just choose these two in nodes, obviously we have to have minimum in 1D problem 2 in nodes. So with these two in nodes, we have two variable in terms of u, that is u1 and u2, that is elemental degrees of freedom, and two constants. So these two constants here and these two u1, u2, they can be related. If we want to increase the number of terms here, let's say to x square, then we need to increase the additional node here and have there also u as a degree of freedom. So then you have 3 elemental degrees of freedom, you can have 3 constants in this approximate solution. So that is about choice of the polynomial. I will also take as an example a 3-noded truss element subsequently, but let me first complete this. So then next step is, like in case of approximate analytical solutions, we were just trying to substitute this in the functional or the weak form and or the strong form, and then trying to find out these constants. Here what we do, because these element nodes are not lying on the boundaries, so and subsequently we are going to enforce the continuity of this u across the elements. So it becomes easier to express these a0, a1 in terms of variables u1 and u2, so that once we solve for those variables, we directly have displacements of the physical quantity at the nodes, and the continuity can be enforced at the time of assembly easily. So the next step is we express a0 and a1 in terms of essentially elemental degrees of freedom. So that is essentially, if you look at here, what we are saying, that u is equal to u1 at capital X equal to 0. We are saying that the value of u at this node is u1. So if you use this, so you can say here in this equation u1 is equal to, when you put this capital X equal to 0, on the right hand side you get a0. So that means a0 is directly u1. So a0 can be interpreted as displacement at node 1 of the element. The second condition would be that u is equal to u2 at capital X is equal to small l. We said the length of the element is small l, so the capital X coordinate of this point is small l. And based on that, you can say that u is u2, so u2 is equal to a0 we have already found out as u1 and plus a1 into small l. So from this you can say that a1 is u2 minus u1 upon small l. And now if you substitute these values of a0 and a1 in this particular equation, so let me say that this is 1, this is 2 and 3. So if you make use of these 3 equations, you can write so finally you get u as a0, which is u1, plus a1, which is u2 minus u1 divided by small l into capital X. And now what additionally we do is we collect the coefficient of u1 and u2 separately. So if you look at the coefficient of u1 is 1 minus x by l. So we have one term here, 1 minus x by l into u1, and then the coefficient of u2 is x by small l into u2. So we can write it like this. Now see, we call these are the nodal degrees of freedom, u1 at first node, u2 at second node, and these are referred to as shape functions, because now these functions, this function and this function, they decide how u is going to vary within the element from u1 at left into u2 at right end. So there is again name for this. So usually we give notation as, let us say, n1 for this shape function into u1 plus n2 into u2. For n1 is 1 minus x by l and n2 is x by l, and these are referred to as shape functions, or sometimes interpolation functions. The name comes from, because these functions decide, as I said, how u varies within the element from left to right. So that is why shape function, because the shape of u, how u varies, or interpolation, it gives you, basically you can calculate using this equation. But once you know u1 and u2, so you can calculate u at any point within the element by putting the appropriate value of capital X. Further, what we would do, usually we write this in the form of a product of basically matrix and vector. So first I'll put, say, the matrix of shape functions n1 into n2, and this vector as, say, u1 and u2. I can write now this equation like this. This I am putting as matrix because although right now it's basically a row vector and this is a column vector, but this can be depending on the problem can be a matrix, but this will always be a vector. So that is why I am writing this. And again we use a notation, so we are continuing with U. This usually we call as interpolation matrix. I denote know this by H. Of course there can be other notation, and into a vector of elemental degrees of freedom. I am using the notation DE. So here H we call as interpolation matrix or shape function matrix, and this D is the, so D, let me write it separately. So DE is the vector of elemental degrees of freedom. So these are the terminologies we will continue to use subsequently. So this is your U. So we call this as H as the interpolation matrix. This is the vector of elemental degrees of freedom. In this case you see this is 1 by 2 and this is 2 by 1. H is 1 by 2 basically in this case vector, and D is a 2 by 1 vector. And then you see we will have to substitute this in the integral functional here. So we need first derivative. So we need to differentiate this U with respect to X. So let us say we call this equation as equation number 4. So differentiating equation 4 with respect to X, we would get du by dx is equal to, see in this you would see H is going to be function of your independent coordinates, in this case X, whereas D is a constant vector because these D consists of values of U at discrete locations. So differentiation means differentiation of this H. So it would actually be dH by dx into dE. And since you know this H is nothing but in this case n1 and n2, so this differentiation means differentiation of each element of the matrix. So dn1 by dx, dn2 by dx into dE. This is what it is, dH by dx, differentiation of each element. We again give a notation to this matrix, what we get here, differentiation of H with respect to X as strain displacement matrix. So we usually denote it by B into DE. So now this B is referred to as, which is giving you finally when you multiply this B with vector of elemental degrees of freedom, you get actually your strain, because du by dx is actually strain. So B is known as strain, or you can say gradient matrix, that also sometimes, because in solid mechanics problem this is strain displacement matrix, in other field problems it would be just a gradient matrix. So let me for the timing say that this is strain displacement matrix. So this is your du by dx. Now finally we need to substitute all of this in the integral functional. So let us look at the integral functional now. Before before I substitute, I also wanted to discuss about, so if you look at these two shape functions n1 and n2, the variation of n1, say if I plot along the length of the element. So if I, this axis let me put as n1, and this is your capital X here. So if you look at n1 is 1 minus x by L. So as we have seen, this is 1 minus x by L. So at small x equal to 0, n1 is unity. So it starts from, let's say, somewhere here, and at x is equal to capital L, this is 0. So as you see, n1 varies from 0 at left into unity at left into 0 at right end. So similarly, if you look at the plot of n2, so if I look at the variable n2, which is x by L, and so this is 0 at left end and unity at right end, so its variation is like so this is how n1 would n1 is varying like this, n2 is varying like this. So and when you take their derivatives, so dn1 by dx is minus 1 by L, dn2 by dx is actually 1 by L, so they are constant. So in this, what you are assuming that du by dx, that is gradient of displacement or strain, is constant within the element. So essentially you are assuming that within the element strain is constant, which would be true if the actually structure is subjected to concentrated forces, but if there are distributed forces, this is not the situation. But with sufficiently large number of such elements, you can still approximate the solution quite accurately. So that's the variation. Sometimes these functions are also known as Lagrange interpolation functions. So these functions are also referred to as Lagrange interpolation functions. Then we want to substitute this approximation of u and du by dx in the integral functional, and since we have expressed u also as h into d and du by dx also as b into de, we have to first rewrite that integral functional so that we can the matrix multiplication should remains consistent. So I, as we have seen, integral half of integral 0 to L, we had EA, then into du by dx whole square. See, du by dx whole square I can also write as du by dx transpose into du by dx. As of now it's actually scalar quantity, so it doesn't matter, this is one and the same thing. Du by dx whole square, if you write du by dx transpose into du by dx, it's one and the same thing. So dx, that's the first term. Then the second term we have is integral 0 to L. Again, see here there is one transpose term, so in this also we want to bring transpose, so u transpose into q dx. Again, no, this is also same thing what we had earlier, that's a scalar, so it is going to give you the same quantity. And the last term, which was q1 into u1 minus q2 into u2, can be written as again in the matrix form. So let me write that as let us say the this one, I am putting a minus sign here. Subsequently we will see that we are going to take it onto the right hand side, although it doesn't matter, you can keep plus here, but for the time you see this is minus, and then here q1 q2 one vector, and then I actually wanted to write the other way around, so first the transpose of u and then this. So let me write that. So I want to write first u1 and u2. So this is actually transpose of de, and then this is, let us say, minus q1 and plus q2. So is this okay? See, when this is going to give you minus here plus, so u1 q1, and the second term would give you minus u2 q2. So what was already there, and the reason for this is going to be clear immediately once we substitute all of these. So we rewrite this integral functional in this form. So this term is du by dx transpose into du by dx, this is u transpose. So what I am trying to make sure that on the left of each expression I have some transpose. So here there is a transpose, here there is a transpose, here there is a transpose. Actually this quantity finally something we are going to take common on the, take out on the left side, so we want to maintain that. And it's the same as whatever original expression you have, so there is no change in the expression. Now we substitute whatever we have got. So now you see what we get is integral 0 to L EA. Now du by dx is v into de. I am going to now use notations. So du by dx I have written as you see here, b into de. So what would be du by dx transpose? Say if you have two matrices, so you would know that product of two matrices A into B whole transpose is B transpose into A transpose. So you can write this du by dx transpose as actually de transpose into B transpose, and then du by dx, which is B into de, and of course then this integration dx. And then this term is minus integral 0 to L, u is again h into d, so its transpose would be d transpose. This light I need to switch off, it's actually reflecting. Babu, can you just check that? Maybe which one is, this one you just switch off, because it is just reflecting, so I am not able to see. So this is d transpose into h transpose into q dx is the this term, and the last term is also I can write, because this is DE was column vector U1 U2, so this is obviously transpose of that. So we have this as actually DE transpose into minus Q1 and Q2. So this is your integral. Thank you. So now you see in this first the integral terms, although in this particular case we know that B is actually a constant matrix, but in general it would be function of x. So but if you look at this vector, which is actually no, a constant vector, we can take it out of the integration. Similarly, this can also be taken out of the integration. So we can rewrite all of this as half, and then I can take out this DE transpose common on the left hand side, obviously because in between these my product of matrices is there, so I can only take this on the left hand side. As of now this is a scalar, so I can write this as half of DE transpose, then integral 0 to L EA and B transpose into B, and then I am keeping this dx. This is actually a matrix which you refer to as stiffness matrix. I will just explain. And then this side also you have DE, that this particular DE. So this DE transpose I have taken on the left side, this DE on the right hand side, and then in the second equation, of course, you can take that as common, so you can write that as DE transpose integral 0 to L and then H transpose into Q dx, and of course the last is as it is, DE transpose into minus Q1 plus Q2. So this is what we can write this, and we call this matrix which you have got here as the stiffness matrix, this particular quantity. So let me give a notation to that. So this we are going to denote the whole of this matrix as element level stiffness matrix. So let me use the notation Ke for that. So then you can write this expression as half of DE transpose, including that integral. I am saying that as Ke into DE, that's the first term, minus second is DE transpose, and this I am going to use another notation. So usually we call this as external load vector, because this is coming from the external force Q. So let me use the notation for this as F external, and this is at element level. So the superscript E is for element, that these are all things for one particular element. So this is D transpose into F external, for no, I am using this F external notation for this variable, and let me call this as internal, because this is no, Q1 and Q2 are the forces from the adjacent element onto this particular element we are considering. So minus DE transpose into, let me call this as F internal for this particular element. So this notation I am using for this vector. So we can write it like this. Now see, this is still what we have is this no, integral functional. Only thing is now it is written in terms of unknown vector DE, and you have this no stiffness matrix, which is this integral, this external load vector and the internal load vector. Now what we say, the solution of original problem is equivalent to delta I equal to 0, because we got no, the big form was written as delta of I equal to 0. So the solution of original differential equation, governing differential equation, so let me just put GDE is equivalent to, or you can say the equilibrium would be satisfied when delta of I equal to 0. So the solution of GD is equivalent to delta of I equal to 0. So now we take delta here, that is, this delta is a variational symbol, and variation of I, this is your I, and variation is always taken with respect to unknowns. So unknowns are here your vector D, which is the unknown displacements at the node points of the element, that is those two U1 and U2. So now when you take variation, see, this is now because in between this matrix is there, and this D transpose this side and D transpose this side. So we use kind of the way we use the rule of product of differentiation or product of two functions. So similarly we do here. So the first, now we want to take variation. So half first variation of this. So let us say delta of this D transpose, then rest of the things go as it is into DE. So this is variation of first into rest of the things when this half is there, plus the variation of second. So you have then D transpose into KE into now delta of dE. So I need to put delta here. So that is delta of dE. So when we take the variation of basically this term, we get two terms. One is variation of this into the second set, and plus the left hand side whatever we have into variation of the right quantity what we have there. So this is a consistent way of basically writing this. And then the minus, of course, this is directly only this term which is in terms of unknown. So that is delta of dE transpose into F external for the element minus again delta of dE transpose, and this is F internal for the element. This is what you get, and this must actually be equal to 0. That is what we are coming from there. That is delta I equal to 0. So now if you see the first set of terms, you actually can see that because dE transpose K dE, and the structure of K is because it's a B transpose B is going to be symmetric. So you would see finally this K matrix is going to be actually 2 by 2 matrix. So you can see this is 2 by 2 and this vector is 2 by 1, and after taking transpose this will become 1 by 2. So finally when we multiply all three together, it is scalar, it's a scalar number, single quantity. If you look at this, the same situation, 1 into 2, 2 by 2, and this is 2 by 1. So when we multiply, this is also a scalar. So that means what we can do, one can be written as transpose of the other, because it is not going to overall, it's a scalar quantity. So a scalar quantity can always be written as its transpose. So what I can do is I can write the second term as the transpose of the first term, and so when you actually write this quantity, this is actually equivalent to this. So that means this can be essentially same as what you have here, the first term. So what I can do is I can know, since dE transpose K delta dE is same, my final result is going to be same, whatever I am going to get delta of dE transpose K dE. So I can write this plus this together. So half then will go. So what I will get is delta of dE transpose into KE into dE. That is, I have eliminated half. Why? Because this quantity is same as this quantity. So I can write this essentially as this. No, I just can take the transpose of this. The second term can be transposed. Still it is going to be same. When you take its transpose, then you get delta dE transpose K transpose equal to K, because symmetric matrix, and then dE transpose would become this dE. So you can combine them together. So this is what you get. So the two terms, that means half goes essentially. So in the result is like, if you have half of d of half of x square, finally get dx x, I can write x dx. Same thing here. But since this is a matrix, so I wanted to write it consistently, that first variation of this, in the second term variation of this. Since these two terms are one and the same, finally a scalar number, so I can represent the second term by its transpose, and when I take its transpose, it becomes same as this. So I can write the two together like I have written here. And then you have, of course, the other two terms as it is, minus of. So let me do one more thing here, that next step, I will take the dE transpose into, of course, this F external E minus delta of dE transpose into F internal E. It's getting repeated too many times. So then let us take the delta of D common throughout, and then what you would get inside is, because this is a, let me put in the vector form. So this is finally what you have is, the first set is KE into DE. I am taking this variation of DE as common on the left hand side, and then what you left with here is F external E and minus F internal E, again equal to 0. Finally it's a scalar number, when you multiply. Now since this delta of DE is arbitrary. Arbitrary means you can know delta U1 can be non-zero, delta U2 could be 0, or otherwise, or both of them are non-zero. But for all possible variations of DE, this quantity must be equal to 0. So now again, for this to happen, the coefficient of this delta D transpose must be equal to 0. That means this equal to 0. So since delta D is arbitrary, we have to make sure that for this to be 0, that entire expression, that is product of this and this, to be 0 means this KE into DE minus F external E minus F internal E, this should be equal to a null vector, that is 0 0 basically. A null vector means it is, I am writing it as 0 0. So what you can do is, this part we usually keep on the left hand side. So you have this KE into DE is equal to F external E plus F internal E. And this equation is referred to as element level governing equation, which is an algebraic equation, because now there are no differentiation and anything in this. So this we call as element level governing equation. Here now KE is the element label KE. If you look back the way we use the notations, this is integral 0 to L EA B transpose into B into dx. This we call as element label stiffness matrix in solid mechanics. Otherwise you can call it as a coefficient matrix. So in solid mechanics we call it as element label stiffness matrix, and it's a 2 by 2 matrix, as I already explained to you. And F external, if you recall the way notation I used, F external was integration 0 to L, this was H transpose into Q dx, and we call as element label external load vector, element label external load vector. So it's more of I am introducing all the terminologies, and the third term here is F in, that is F internal for the element. So we call this as, which is essentially minus Q1 and plus Q2, and this is referred to as element label internal load vector. So this finally we get this what I just wrote, this as the element label governing equation. This is element label stiffness matrix, external load vector and internal load vector, and they are defined by this. So this is the element label stiffness matrix, external load vector, and this is the internal load vector. So this is how the briefly the steps involved in deriving the element label governing equation. So you start with if you have a differential equation, then you get the weak form or the integral functional, then assume an approximate solution, express the approximate solution constants in terms of nodal degrees of freedom, substitute that in the integral functional, take delta equal to 0, you finally get to the element level governing equation. So the next step, to see the next step, that is assembly, to solve a problem, let us evaluate this for a simplified case. So assuming that if EA is constant, then if you look at the K can be written as which is it can be taken out of the integration, of course, which is EA integration 0 to small l B transpose. So B is as you have seen, the B transpose is going to be dn1 by dx dn2 by dx. This is your B transpose into B, which was dn1 by dx dn2 by dx, and then integration with respect to x. So what I have done, saying that EA is constant, I can take it out of the integration. This is here B transpose into this is B. Since B is a row vector, the B transpose would become a column vector. So since dn1 by dx and dn2 by dx are also constant, so when you multiply, obviously this is going to now this vector is a 2 by 1, this is 1 by 2, will give you a 2 by 2 matrix. That already I told you. So when you now multiply all of these, so dn1 by dx into dn1 by dx, so if you look at the various elements of this matrix, integral 0 to L, what you will get is dn1 by dx whole square, second would be dn1 by dx into dn2 by dx. When you multiply this, you get dn2 by dx into dn1 by dx and dn2 by dx whole square, then integration dx. So this is what you get after multiplying these. And dn1 by dx is minus 1 by L, dn2 by dx is plus 1 by L. So when you put all of these and do the integration, so the again integration is actually means integration of each element. So that is integration of this. You can take this integration inside in each of these terms. Right now it's a simple problem, but I wanted to demonstrate you all the steps. So the meaning of this integral is essentially know that integration of each of these terms. So that is integral 0 to L dn1 by dx whole square dx, integration 0 to L dn1 by dx dn2 by dx dx, and so on. So similarly these two terms. And when you do this integration, so this is 1 by L square, integral would be 1L. So what you finally get is EA. Here dn1 by dx square is 1 by L square. Its integration 0 to L will give you essentially in result as 1 by L, and dn1 by dx into dn2 by dx would be minus 1 by L square. So its integral is minus 1 by L. Same way here minus 1 by L, and this would be plus 1 by L. So you get the stiffness matrix as if you take this 1 by L common. So a scalar common means you take out from all the elements of the matrix. So it is EA by L 1 minus 1 minus 1 and 1. So this becomes your stiffness matrix for element level stiffness matrix for a two noded truss element with EA as a constant quantity. If EA was a function of x, then you have to keep it inside the integration and do the integration accounting for the variation of EA as a function of x. Now let's look at the external load vector. So F external for the element, by definition we had said no that this is integral 0 to L H transpose into Q dx. So as you see, assuming that Q is constant, that means the rod is subjected to a constant distributed force. So then I can take this Q out of the integration, Q integral 0 to L, then H transpose, H is N1 N2, so its transpose would become N1 N2 like this, and then this dx, Q have taken out. N1 is 1 minus x by L and N2 is x by L. If you do their integration, finally what you will get is Q into this I am writing as a vector. So integral N1 is 1 minus x by L, its integral you will find that will turn out to be L by 2. You can check, no, 1 minus x by L, what is the integral? Similarly this also will be L by 2. So you can know L by 2 can be taken out, so you can say QL by 2, 1 and 1. And if for a distributed load, if we derive the external load vector consistent with the interpolation function, we call this as consistent load vector. There is another term, consistent load vector. Meaning of this consistent is that this is directly derived by taking the shape functions into account. Although there is another approach of for distributed forces known as lumped load vector. So in that you calculate the total load and maybe one base that equally distribute in all the nodes. In this case the lumped and the consistent load vectors would be same, but in general they are not. In this case, like what I am saying is that Q is the force per unit length and the length of the element is small l. So the total force is Q into small l. There are only two nodes, so if equally divide QL by 2 first node, QL by 2 second node. Same thing we are getting here, QL by 2 for the first node, QL by 2 for the second node. So in this case the consistent load vector and the lumped load vector they are same, but in general they could be different. So we call this load vector as a consistent load vector, which happens to be same as lumped load vector. So this is the external load vector. Now when we want to do the next step, that is assembly. So see, the assembly means what we want to do is we are discretizing the given problem into a number of elements, and then what we wrote right now was the element level governing equation. If you look at the element level governing equations, what are the unknowns there? So if you look at the structure here, what I wrote at this particular in equation, unknowns are, one is D, which has got two unknowns, that is value of U1 and U2, and of course this is known because this is in terms of known quantity Q and length of the element. And again internal force vector is also unknown because we do not know what are the reactions of left and right elements on this particular element. So you see there are 4 unknowns, U1, U2 and Q1, Q2. 2 equations only we cannot solve. So we need to basically assemble all the elements together, then only we would be able to solve these equations. So the purpose of assembly is so that we are able to solve the equations. So essentially this it facilitates the solution of equations, that is to generate finally we equate the number of unknowns and number of equations. The how we do it, so next question is how. So we do 2 things when we try to assemble the element level governing equations of different element. One is we impose the continuity of primary variables which are no degrees of freedom at in nodes. So impose the continuity of primary variables. That is one. And second is actually the summation of forces acting at the node points. So these are the 2 things we actually do when we are doing assembly. So now how one is the we are going to say that the primary variables must be continuous, and we'll see how we do that. So let me take a simple example, the same of course the problem, but discretized into only 2 elements. So because we are assembly means we are assembling all the elements together, so we have to refer back to the discretization. Right now without putting the boundary condition, let me say that we have discretized the entire domain only into 2 elements. So this is the first element, this is the second element. Each element has 2 nodes, but then we have to have a global node numbering. So let us say the global node number for this is 1, for this is 2, this is global node number 3. So element is 1, this is element 2, this is a global node number 1, this is node number 2, this is node number 3. Because we are discretizing the structure into 2 elements, so we will have 2 elements and 3 nodes. They are the connecting points as you see here. And if you look at locally, the first element is defined by first and second global node, and second element is defined by second and third global nodes. Okay. So overall, if you look at in terms of displacements, you will have essentially 1 degree of freedom here, that is value of u. Now when you look at 2, because 2 is one side, there is a left side element number 1 is coming, and the right side element number 2 is coming. And we had in both that means right end of 1 and left end of 2, we had some u, that is a degree of freedom at that node, either the second or the first element or the first node or the second element. Now what we are going to say that value of u here, whether you consider u2 of this or u1 of this, let us say that they are same. That is how we impose the continuity of primary variables. Our u in this case is a primary variable. So I would say that u2 of the first element and u1 of the second element, they are same. So that is how at the common nodes we are enforcing the continuity of primary variables. So that means then I will have only 3 displacement unknowns, one at this node, one at this node, one at this node. This value of u here is common to both this element, the right as well as the left element. So if I now look at the structure of these equations, so what I will have, the final system would be like this, that I will have the structure is going to be similar to element level governing equations, but the total displacement unknowns, if you look at value of u at this point, let me call as u1, the value of this node as u2, value of at this node as u3. These are the global node numbers. For the first element u1 and u2, for the second element they are actually u2 and u3. This is the left hand side. The right hand side again, because it has to match with the number of rows here, so external load vector contribution would lead to column vector of 3 elements, and internal load also will lead to a column vector of 3 elements. A element means the elements of a matrix, what I am referring to. So now how we do assembly is we look at the connectivity of elements. So this is just the structure of equations what we would get when we join all of the elements together. So now if you look at connectivity, and that is if you look at element number 1, so essentially what I want to say by connectivity is that is starting node and in node. So starting node is global node number 1 and in node is global node number 2. Because we have 1 and 2 in the element level is basically in this case starting and in nodes. If you look at element number 2, its left in node, that is starting node for element number 2 is the global node number 2 and the in node is global node number 3. So this is their connectivity. Okay. So since we see the element number 1 consists of global node 1 and 2, therefore the contributions of first element would go to first 2 rows and columns of the matrix here, first 2 rows of the vectors here and here. So if you look at the, now let us also assume that both the elements have got the same length, small l and small l, which is half of the total length. So in this equation I can take out EA by L common throughout. If it is different, either EA is different for the 2 elements or L is different, you have to keep them inside. So for the timing, let me take it as EA by L out here. So you just, because the first element is consisting of global node 1 and 2, so first 2 rows and columns will be occupied by the first element here. So first, if you look at the element level, first row and column of the element stiffness matrix goes to first row and column of the global matrix, that is here, and EA by L is taken out, so this just becomes 1. Then element stiffness matrix, first row second column, that is if you look at here, this is first row second column of the element level stiffness matrix. This goes to first row and second column of the global matrix, so that is here, which is actually -1. Then we come to the second row of the first element. So again you have that, so second row of the first element is -1 and 1. So -1 goes here, that is second row first column goes to global, second row first column, and the second row second column of the first element goes to global, second row and second column, that is here. So this is the contribution of first element onto the global stiffness matrix. This we are going to define as global stiffness matrix. Then now we will have to bring in the contribution of second element. Now the second element is defined by the, actually starting node is global node number 2 and in node is global node number 3. So at the element level still you have a 2 by 2 stiffness matrix. So first row first column, first row second column, second row first column and second row second column. So for the second element, in this case the stiffness matrix is same as first element, but its first row first column of the second element will go to second row second column of the global matrix. So you add here, now it's addition. Then the first row second column of second element will go to second row third column of the global matrix, and that is actually -1, so it will go here. So if you look at the structure of element level stiffness matrix, which is EA by L, 1, -1, -1 and 1. This is what I am talking about. For the second element, see this is the first row second column, it is added here. For the first row second column you are adding here, then you take the second row, so second row first column will go to second row second column here. So third row and second column, because no, the second node of the second element is node number 3. So this element of the second element stiffness matrix would go to third row and second column. Then this will go to third row third column, so you add it here. So this is 1 -1 -1 1 is the contribution of first element to the global stiffness matrix. This is the contribution of second element to the global stiffness matrix, and these terms are actually 0. So wherever nothing is there, it is actually initially initialized to 0. So there is a, obviously you see, here there is a addition at this second row second column, you get the contribution from both the elements. Then coming to the right hand side, so first is external load vector, which is QL by 2, QL by 2 for both the cases. So again for the first element, first row goes to first row of the global matrix, second row goes to the second row of the global matrix. So what here you have is QL by 2 and then QL by 2. You're just putting the first row, second row of the local element. Then when you go for the second element, Second element actually starting node is global node number 2. So we will add its contribution here, QL by 2, and then QL by 2 here. That is second row and third row of the global load vector. That is here and here you are adding the contribution of second element. Similarly, if you look at the element internal load vectors, so the first element is, now in the internal load vector what I am going to do, because in general at the common nodes the internal forces on the left and right could be different whenever there are external forces. So I will just differentiate those. So this is for the first element, it is Q1. This was already there, I am putting on superscript 1. That one is that it is coming from the first element. And then here you have Q21. So this is the, in the external load vector we had minus Q1 and Q2. So they are going to the first row and the second row. For the second element they will go to the second row and third row. So again here we will have minus Q for the second element. So still I am putting the subscript as 1 but the superscript as 2. And then for the second element, second row of the internal load vector is Q2 and superscript 2. So this superscript 1 here and 1 here for the element, and this superscript here for the second element. And this 1 and 2 we have used in the element level governor equation. So only thing I have done here is I have just introduced one additional superscript here in the internal load vector, 1 for the first element, 2 for the second element. So you see here that in the stiffness matrix there is addition here, there is addition here, there is addition here. This we call as the assembled system, or system level equation. In that this is known as global stiffness matrix, and this is the global external load vector, this is the global internal load vector. Okay, so is this clear assembly? So very important thing here is the connectivity. That is, know how, what is the starting node of the first element, in node of the first element, starting node of the second element, and in node of the second element. I am going to proceed further, but what you can try is, suppose we do the global numbering differently. You try as an exercise that if the numbering is done differently, that differently means instead of giving the global numbers as 1, 2 and 3, let me say this is element 1, this is element number 2. This is 1, but this is global node number 2, and this is global node number 3. Now the connectivity for the first element, it is 1 and 3, for the second it is 3 and 2. So try doing the assembly. That no, then you will see that the first element, first row will go to the first row, second row would go to actually third row of the global matrix. Similarly the columns, first element, first column will go to the first column, and second will go to the third column. When you go to the second element, first row will go to third column of the global matrix, second will go to the actually second. So you can just do this exercise when you have this kind of a numbering, how the assembly is done. So this is assembly. So once we do the assembly, then next is the imposition of boundary condition and solution. So this is the assembled system. Now we come to the boundary conditions. Boundary condition in this case, what are the boundary condition, the problem I started with? This is as an exercise, so you'll have to do the exercise. For assembly. Now next is what comes as imposition of boundary condition. So see, in this case what we have actually done is we have summed up the one is that we have imposed the continuity of primary variables. That is, at the common node we have said both the nodes whether belonging to first element or second element have same u. So that is how you are enforcing the continuity of primary variables. Second is you are actually summing up the forces. So that summation is happening only at the second node, because that is the only common node between right now for these two elements. So then next what comes is the boundary conditions. So now the boundary conditions we look at is the left end, if it is fixed, that the way I started initially stated the problem, that it is fixed here and then there is a distributed force. So here your u is 0, that means u1 will actually be 0, because u1 is node 1 is here and there the rod is fixed, so u has to be 0. So one boundary condition is that u1 equal to 0. So one is this. Now what else? Still if you look at in these equations, so now u1 is known, which is 0, u2 and u3 they are unknowns, and this side if you look at this as of now the way we have written there are 1 2 3 4, so still we have 5 unknowns, only 3 equations. So we look at what would be the value of now Q22. This is the value of now force at the right end. Q22 is here, this is equal to actually 0. So second now condition is that Q22 is equal to 0, that is actually du by dx is 0 at the right end of the rod, and therefore Q22 is actually Ea into du by dx, but not the approximate solution, but actually that's a real solution. So that is why we are writing as a force, we haven't written it from the approximate solution. So Q22 is 0. Now what about the intermediate node? So the intermediate node is that is at the center here. To interpret this summation Q21 minus Q12, we need to draw the free body diagram of actually node now. So let me draw the FBD of, I think that is where I will stop. So FBD of node 2. So if you now I want to draw only the FBD of the node 2 here, so just left of that let me take a section, and just right of that also let me take a section, and then draw the free body diagram. So this is just the location where your node 2 is lying. Now what are the forces acting on this? Yes, what are the forces? If you look at the first element, I had drawn for a general case the free body diagram of the element. The first element, this is here Q1 1, and this is here Q2 1, and in of course it had a distributed force here. This is for the first element. For the second element, if you look at the similarly free body diagram, this is going to be here for the now second element, so Q12, and this is Q22, and of course it has a distributed force. So since we are talking of this common node here, see now you can think of this Q21 as the force exerted by node onto this element. So opposite of this is going to act actually here. This is the first element, this is the second element. So I can show here when I draw the free body diagram of the node, this force in the opposite direction. Similarly, if you look at this Q12, this is the, you can think of this is the force acting on the second element exerted by this node, so that is in this direction. So the element itself would exert a force, this Q12, in that direction at the node. So this is this is in the opposite direction of this. Similarly, this is in the opposite direction of this. This is a free body diagram of just node 2. And if there was an externally applied concentrated force there, which is right now 0, so let me say that there is also externally applied concentrated force, let us say P. Now this completes the, although in this case P is 0, okay, the problem be considered, but this is the free body diagram of the node. So these are the free body diagrams of the elements, and this is the free body diagram of the common node, which is here. Now this node is actually common global node between these two elements, that is right end of this and the left end of this. This is the free body diagram here. And since the entire structure is in equilibrium, so each and every part has to be in equilibrium. So we apply the sum of forces along x direction equal to 0 for this. So you get Q12 plus P, this is in the opposite direction, so minus Q21. As a section forces, again these are positive, but when I am writing sum of the forces, you consider the positive in, say in this case, plus x direction, and this is equal to 0. Then the difference what was coming in the equation here, Q21 minus Q12, so you can write this as Q21 minus Q12 is equal to P, and P is 0 in this case, so what you get is finally this equal to 0. So this is the second boundary condition. Finally you can say the third boundary condition for this case is essentially Q21 minus Q12 is equal to 0. It is very important, although see, as far as the imposition is accounting for this external force is concerned, you can simply, because if this force P is along the positive u direction, you directly add at the corresponding node rho, that is second row in this case because it's a second node, but its origin comes from the free body diagram of the node, then its equilibrium equation, and then writing this internal force difference in terms of the external force. So many other textbook they might simply write that there is external force. So you just start at that particular node, external force, whether positive or negative depending on what is the direction of the force, but the proper derivation is this accounting for the internal forces. So now if you see in these equations, so I think we would continue in the next class. I just want to finally tell you that this u1 equal to 0, and of course, and this q2, this is equal to 0. This will not be 0 because no, this is a primary variable at that point, this is secondary variable. So once this is 0, this cannot be 0. So unknowns are now u2, u3, 1, 2, and this I just sum, we know it's equal to 0. This is unknown, so this is the third unknown, this is 0. So now we have three, accounting for the boundary conditions, we have 3 unknowns and 3 equations. What you can do is first take the second and third equation, solve for u2 and u3, and then take the first equation and get your q11. So this is how the further solution would proceed. So we'll continue in the next class. Please repeat this thoroughly. These are the very basic steps, and you should be clear about how we do all of these. If you have any doubts and questions, you can ask outside the class.